In previous lecture we have finished with the various modes of vibration in the given molecules. So there are the various of the different type of arrangement in the molecule that will take place. So various types of various types of vibrational motion, there are the either stretching or bending type of vibration in the given molecule, and also there are the symmetric, unsymmetric, and the twisting, wagging, rocking, and the scissoring type of bending in the given molecules. Okay, now we need to next consider the how that vibrational motion will changes the frequency, and how that exactly the frequency of vibration matches with the frequency of IR radiations, so that we can have the resonance of the given molecule with the radiations, and finally we get the absorption and we'll measure the radiations that are absorbed by the given molecule. So in order to consider that, we need to first consider the what actually happening in the stretching of molecule or the vibration of molecule. So in order to consider that, we'll consider again the same model, that is spring and ball model, and we'll try to apply the Hooke's law for that Hooke's law you might have studied in the physics. Okay, so we just apply that Hooke's law for the stretching of that particular spring model, and based upon that we will try to derive the frequency relation with the radiations of the given molecules. Okay, so now in order to derive that, consider the diatomic molecule with the atomic masses M1 and M2, which are joined together by the chemical bond. The bond is being comparable to the spring with the it is atom at their ends. So the elasticity of the spring, which can be determined by the factor which is called as a force constant. So in this, all this IR spectroscopy or this derivation, this force constant will play as an important role. So what do you mean by the springs constant or the force constant? The elasticity of the spring, which can be determined by the factor called as the force constant. So force constant is important for the determining the elasticity for the given uh, spring or say bond. Okay, spring or bond. So such a spring which can be put into a vibratory motion by stretching it and releasing it to the spring. If the vibrations are being the simple harmonics, then the Hooke's law which can be applicable to such system. So according to this law, the restoring force F will pull the or push the spring to its equilibrium position, so that the displacement is x. Okay, so consider F is being the force of that pulling or pushing to the spring, and x will be the displacement due to the force F. So we know that this force is what directly proportional to the displacement. So whatever the amount of force we have applied to the system or the spring, that much amount of displacement will occur in the given spring. But we also know that this, if we consider the, suppose this is the spring. Okay, and if we apply the force in this direction, then what will be the result of this? Result of this will be the displacement in the opposite direction after we release this force. So after we have released this force, so we just remove this force, so that the displacement will be in the opposite direction of that force we have applied, because it will be try to stretch the its full length. Okay, and try to become at an equilibrium position. So we can say that force is directly proportional to the x, but with minus sign. So minus sign indicating what? The direction of displacement. So the force and displacement are always in the opposite direction. So here we should incorporate the negative sign. Okay, so we can have the f which is directly proportional to minus of x, or simply we can say that f is equals to minus of k into x, where this k is nothing but the proportionality constant, which is called as a force constant. Okay, so this k will be important parameter or the important constant, that is the force constant. So in this equation, F is being the restoring force, K is being the force constant, and X being the displacement. So negative sign indicate that the force is being what? Restoring force, and thus the direction which is being opposite to that of the displacement. Thus, so when the displacement is equals to 1, the force constant will becomes to what? The force. Okay, so force become force constant. So we can say that the force constant, which can be defined as the restoring force per unit displacement. Okay, so force constant can be defined as the force per unit displacement. The stretching and compression of the bond, which may be assumed to be the similar to that of spring and bond model, which will obey the Hooke's law. Thus the restoring forces, which tends to bring about the atoms to the its equilibrium position, then the force constant, which is the measure of what, the force which is required to bring about this stretching of a bond. So higher the value of force constant, stronger will be the bond. Okay, so most important thing that the magnitude of this force constant, so higher the magnitude of this value of force constant, the stronger will be the bond. So bond will be the stronger one. And also if bond is being stronger, means what, it will vibrate at a higher frequency, because higher the strong bond, or the higher the strength of the bond, higher will be its vibrational frequency. So here we are considering the two extreme cases, that is, suppose this is the stretching of spring or the atom bond, and this is the contraction of the bond. Okay, so the equilibrium position is likewise. So if we have like stretch or compress the bond, then release that, so there will be the fixed time where this equilibrium position will be reached. Okay, so every time either stretching or the contraction, the after we have like reached to the equilibrium, the bond distance will always be in this much. Okay, now next is the vibrational frequency, or the frequency of vibrational motion. Now the stretching or compression of the chemical bond has resulted into what, the vibrational of the constituent atom about its mean position. Hence such vibrating molecules is called as what, the harmonic oscillators. So for simple harmonic vibrations, the frequency of oscillations omega, which is depending upon the reduced mass m of the system, and hence the force constant k, which can be calculated based upon the various terms like okay, this is the vibrational frequency of oscillation for the simple harmonic oscillators, and this k is what, the force constant, and mu is what, the reduced mass. So this vibrational frequency of oscillation omega is given by 1 upon 2 pi into under root of k upon mu. And in terms of wave number, we know that in order to find out the wave number, the we need to just simply divide by what, the speed of light. Okay, so the wave number, which can be obtained by simply dividing by the speed of light, that is c. Okay, now for the simple diatomic molecule, we know that this reduced mass is what, m1 m2 upon m1 plus m2, where this m1 and m2 are the atomic masses of the two atoms that are involved in the stretching or compression. Now according to the wave mechanicus, the vibrational energy level in this atomic diatomic harmonic oscillator, which can be given by these simple formulas. Okay, so all these derivations are like there in the quantum mechanically derived, so we are not going into the details of derivation for these formulas. Okay, so just remember the final formulas, which will be useful for the spectroscopic term. If you are like going detail into this spectroscopic derivation, we can get that derivations from the quantum mechanics. So this there we are having what, in the vibrational so rotational spectroscopy, the energy is depending upon the rotational constant j and uh, that separation constant b. Okay, so that j is nothing but what, our the rotational quantum number, so that also will be obtained from the quantum mechanics. And same this vibrational energies also can be obtained from the quantum mechanics. So we will directly use the formulas here. So vibrational energy is directly given by what, ev is equals to v plus 1 by 2 into h omega, or simply we can say that h nu. Okay, if we like simply represent this omega by nu, that is frequency, simple. And this ev can also be written as the 1 v plus 1 by 2 hc nu bar or omega bar. Okay, so where v is the vibrational quantum number, this v, and which can have the values from 0 1 2 3 up to so on. And omega bar is what, the vibrational frequency in the wave numbers of the molecule, and h is Planck's constant, c is the velocity of light. Now the various vibrational energy levels can obtain by using various values of V. So for V is equals to 1, the vibrational energy level is what? 3 by 2 Hc omega bar. For V is equals to 2, vibrational energy level is 5 by 2 Hc omega bar. For V is equals to 3, it is 7 by 2 Hc omega bar, and for V is equals to 4, it is 9 by 2 Hc omega bar. So from the above equation, it can be observed that the vibrational energy levels are being equally spaced. Okay, so there is a equal space between two vibrational energy level for the simple harmonic oscillator, okay, or the diatomic molecule. Now for the 0 point energy, because here we have not considered V is equals to 0. Okay, so if what will happen if the V is equals to 0? So previously we have seen that if J is equals to 0, then what happen? The rotational energy of the molecule will become 0. Okay, but what happen when the V is equals to 0? So that we need to consider as a 0 point energy. So as seen earlier, for the molecule undergoing the simple harmonic oscillation, the vibrational energy is given by what? This V plus 1 by 2 Hc omega bar, where this V is the vibrational quantum number, omega bar is again the vibrational frequency in the wave number of the molecule, and H is what? The Planck's constant. C is the speed of light. So for the lowest vibrational energy means what? At 0 point, that is V is equals to 0, the energy level of the molecule is given by 0 plus 1 by 2 Hc omega bar, or 1 by 2 Hc omega bar, and this for omega is what? 1 upon 2 pi c into under root of k upon mu. Okay, so we can see this energy at when this V is equals to 0 is not equals to 0. Okay, so it has certain value, which is what? H upon 4 pi into under root of k upon mu. So it is depending upon the force constant k of the bond, as well as the reduced masses of the atoms that are involved in the given molecule. Okay, so this implies that even at absolute zero temperature, when all the form of motion such as rotational motion, translational motion are ceased down, the molecule will still possess the some vibrational energy. So even if we have cool down the temperature up to 0 Kelvin, at that temperature we will expect that all the motions of the molecule should be ceased out. Okay, means that motion should be stopped, but in actual practice we expect some vibrational motion in the molecule even at absolute 0 Kelvin. Okay, and mathematically we can say that this absolute zero values, or the absolute zero energies, can be obtained by h upon 4 pi into bracket under root of k by mu. Okay, so this energy which cannot be removed from the molecule by even after the cooling also. So in other word, you can say that at any temperature the atoms in the molecule which can never be completely rest relative to each other. So this 0 point energy will depending upon the vibrational frequency, so omega bar of the molecule, and hence on the strength of the molecule, and the chemical bond, that is the force constant. So in classical mechanics we would say that the molecule will be having no vibrational energy at absolute 0 Kelvin. We are expecting that, but however, according to this quantum mechanics or wave mechanics, the molecule will possess the some 0 point energy which is not a zero. Okay, so there are certain postulates in the quantum mechanics. Out of that, one is the Heisenberg's uncertainty principle. So in according to this principle, this is impossible to determine simultaneously exact position and the momentum of the particle. So likewise we can say that this uh, motion and the force constant or reduced mass will define the 0 point energy in the given molecule. Okay, so here is one numerical based upon this vibrational motion, which is a simple numerical, which uses what the simple formula, that is 1 0 point energy Hc omega bar. Okay, so in next lecture we will try to see some selection rule for the vibrational spectroscopy and the vibrational spectra for the real molecules. Okay.